Welcome back to Ray class. I'm Engineer Shegun, and today we're talking about simple AC circuit. The first thing I would like to bring across to you is the meaning of AC, alternating current. Now, you must have heard me talking about direct current too. There's a difference between alternating current and direct current. The basic difference between the two of them is that direct current travels in a particular direction. That's where it earns that name, direct current. Alternating current does not just move in a single direction, it goes back and forth. So if I were to have a wire, for example, like this, if I let me just extend it and draw a terminal like this. Now, if whenever you are dealing with any battery, any cell or battery circuit, there will always be a positive terminal and a negative terminal in there because the current flows in a particular direction. But if you have a wall socket or a socket that you need to plug into a wall, for example, you don't get to see plus and minus there. You can plug it in any direction and it works. Why? Because the alternating current moves back and forth. At one moment, yes, positive, yes, negative. At another moment, yes, positive, and yes, negative. It changes back and forth. It goes back the wire, comes forth, goes back like that. That's how it moves. And it does not just move with the same amplitude. It increases, gets to its peak, stops, reverse, go back, get to its peak, stop, like that, like that. And that's why we can represent an alternating current by this sine wave form, like this. It does not mean the current is moving like a snake in the wire. It's going back and forth, the wire, back and forth, back and forth. But just that as it's going forward, it gets to its peak, it's increasing. It gets to a peak, its peak, which is the peak current or the maximum current. Then it reverses. It slows down and gets to zero again. Then it reverses and moves in the opposite direction. So that's why we are doing it like this in this format. And of course, if there's alternating current, then there will be alternating voltage because there's no current without voltage. And I can also draw a graph of voltage too, like this in this format. And you get to a peak voltage, then here's zero, here's the peak voltage in the opposite direction, and like that, like that. This is time, by the way, a graph of current versus time, a graph of voltage versus time. Now, because the current is not stable, but we don't see it with our naked eyes because this is happening so fast. Because it's not stable, meaning that we can have a particular amount of current at a particular time. The current at a particular time is what we call the instantaneous current. And you can write an equation for the instantaneous current, the current at a particular time, and also there's an instantaneous voltage, the voltage at a particular time. The current at a particular time is actually given by I is equals to I naught sine WC. Where W is the angular speed or angular frequency of the alternating current. You may not fully understand angular frequency. Angular frequency is quite different from frequency itself. But for your level, let's just stick with angular speed of it. That's how fast it's changing or breaking one complete circle. Now, by the way, you should know that W is 2 pi f. So I can also say that I is what? I naught sine 2 pi f, then C. The whole of this place from here to here is the phase angle as well as this. So this is how I can represent an alternating current. I is instantaneous current and I naught is the peak current. I can do the same with voltage. An instantaneous voltage will also be V is equals to V naught sine WC. And of course I can also say 2 pi ft. Instead of writing W, I can say 2 pi f. So this is also very important. And this is also very important. There's something called the root mean square current. And this is the definition for the root mean square current. The root mean square current of an alternating current is the current is the steady current that will produce the same amount of heat, that will produce the same amount of heat in the same resistor at the same time. That is the root mean square current. Now, the root mean square current can be represented by this equation. IRMS, root mean square current, is equal to I naught divided by the square root of 2. And I can rationalize this solved, and then I can also have IRMS is equals to root 2 I naught divided by 2. That's if I rationalize. And there are several ways I can express this guy. I can just punch this in my calculator and get a different value. I think 0.707 something I naught. So it's very important to know this. You should also know that the root mean square current and alternating current is the DC equivalent. So when you are running your pressing iron, when you are using your pressing iron, what is actually eating up that electric iron? It's not the iron, it's actually the root mean square current. Again, if there's root mean square current, there will be root mean square voltage. And root mean square voltage is given by the expression VRMS is equal to V naught divided by square root of 2. And of course, I can still rationalize this guy and I'll have something like this. Now, the next thing I would like us to talk about is impedance. I'll talk about impedance, then I'll take some couple of questions. But let's talk about impedance. Now, what is impedance, by the way? We are going to talk about impedance. And of course, before impedance, we need to talk about reactance. In the past, we have talked about resistors, and then we talked about resistance. In the past, we said that resistor is a device that opposes the flow of current. Right? The resistance is that opposition to the flow of current. So, when it comes to alternating currents, it's not only resistors that can oppose the flow of current. Capacitors can also oppose the flow of current. Inductors can also oppose the flow of current. But we do not want to call the opposition to the flow of current by a capacitor and an inductor as resistance again. So we decide to call the opposition to the flow of current by a capacitor or an inductor as reactance. So if the opposition to the flow of current is due to a capacitor or due to an inductor, we call it reactance. So there's capacitive reactance and there's inductive reactance. So if I mention capacitive reactance, then I think you should have an idea of what I'm talking about. Capacitive reactance is not the opposition to the flow of current brought by a capacitor. Capacitive reactance, capacitor. Then inductive reactance will now be the opposition to the flow of current brought by an inductor. Inductive, from inductor. Now, how do we express capacitive reactance and inductive reactance mathematically? Mathematically, we can express it by this equation. We can say that capacitive reactance XC for capacitive reactance and XL for inductive reactance. This is given by 1/2 pi FC. 1/2 pi FC. Recall that I said that 2 pi F is W. So I can also rewrite this as saying XC, capacitive reactance, is equal to 1/WC, because 2 pi F is W. For inductive reactance, I can say that inductive reactance is equal to 2 pi FL. Again, 2 pi F is W. So I can also rewrite it as saying XL is equal to WL. That being said, the next thing I like to introduce, remember XC is capacitive reactance and XL is inductive reactance. Let's now talk about impedance. Now, what is impedance all about? Remember I said that resistors bring an opposition to the flow of current, capacitors and inductors in an AC circuit bring about an opposition to the flow of current. So what about if I have a circuit that has a resistor and a capacitor? Or a circuit that has a resistor and an inductor? Or a circuit that has all these three, resistor, inductor, and capacitor. All of them will work together to bring about an overall opposition to the flow of current. So listen carefully to what I'm about to say. Therefore, I can say that impedance is the overall opposition to the flow of current brought by the combination of a resistor and an inductor, or a resistor and a capacitor, or the total combination of a resistor, inductor, and capacitor. So, in other words, I can say that impedance is simply resistance and reactance. And of course, there are two reactants that we can have. So the symbol we use to represent impedance is Z. And then I can say that impedance Z is equal to the square root of R squared plus XL minus XC all squared. So that is impedance. In a case where I only have resistor and inductor, that means I only have resistance and capacity and inductive reactance. That means XC will be equal to 0. I just have R squared plus XL all squared. In a case where I only have resistor and capacitor, meaning that I will only have resistance and capacitive reactance, XL will be 0. So that my equation will be R squared, square root of R squared plus XC all squared, because of course, if this one is 0, I'll get minus XC all squared. Minus times minus is plus, so I'll just get R squared plus XC squared. So that is for impedance, and that's how you calculate it. And if they give you both of them, you can just calculate this one individually. I don't want to write this other equation because I don't want it to be complicated to you, because this is all you need to know. So if somebody should come and the person wants to try to look very smart, the person can just say Z is equal to square root of R squared plus the person can say 2 pi FL minus 1 over 2 pi FC all squared. And you want to be feeling that this is special. There's nothing special here, because we already know that XC is 1 over 2 pi FC, and XC rather is 1 over 2 pi FC, and XL is 2 pi FL. So there's really nothing special here. I'm just putting in the values. So you don't need to memorize this and memorize this. Once you know this and you know this and you know this, you are good to go. You can always reproduce this and regurgitate it from your mind at any point in time. So that being said, how can we apply Ohm's law to all of this stuff that we have said? Remember, I'm just calling this guy capacitive reactance, and I'm calling this guy inductive reactance, and I'm calling this guy resistance. Either ways, they all are doing the same thing and they mean the same thing. They are opposing the flow of current. So all of their units from XC to XL to I is in ohms. Ohms, I mean ohms, or the symbol ohms. So they are more or less like resistance to Riemann. So that means I can apply Ohm's law to any of them. What is Ohm's law, by the way? Ohm's law is simply that V is equal to IR. But it's not only R that is resistance or that opposes the flow of current. What would that opposes the flow of current? XL. So I can say V is equal to I XL. This one is just replacing this one because both of them are doing the same work. Is it only XL that opposes the flow of current? No. XC. I can also say V is equal to I XC. It's not only XC. I can have the total combination of them, and I can also say V is equal to I Z. It all depends. And you already know that there are two types of V and there are two types of I when we are talking about AC. There is the instantaneous currents. In fact, there are three types. There is the instantaneous, but they will not bother you most of the time with the instantaneous. There is the instantaneous, there is the peak, and there is the root mean square. So I can say V naught I naught. Yeah. I can say VRMS, IRMS. It's not a big deal because it's root mean square voltage to root mean square current, of course. Or it can be peak voltage to peak current. I'm applying Ohm's law, and I can do the same thing with this and with this. I can do the same thing with this and with this. I can do the same thing with this and with this, depending on how the question comes. So what we'll be doing now is taking question on this and see how you can play with them. The thing I always try to tell students is physics is not really very difficult. It's easy. All you just need to do is not to compartmentalize things. It's a continuous flow. Just understand, like the way I've explained everything. Do not just say, okay, this is where it is, I should memorize this formula. Know where it's coming from, and you will see that there's something that you already know in the past. It's not a new thing. So let's take questions so that we can wrap our mind around it and we can understand the intricacies in it.